Units of measurement. Units are very important, and one of the things that is sort of a pet peeve of mine is students tend to just leave the units off. They'll pay attention to the numbers and they'll do all these great calculations, and then they'll come up with the wrong answer because they didn't take care of the units. It's not just students that do this. Back in 1999, NASA lost the Mars Climate Orbiter because of miscommunication over units. One team was doing calculations in centimeters and one in inches, and as a result, the orbiter was too close to the surface of Mars, and it got pulled into the by the gravity, and it burned up. $125 million mistake over centimeters and inches. So we don't want to be that person, right? Of course, there was an investigation. They concluded the root cause of the loss of the spacecraft was a failed translation of English units into metric units. Units are very important. So let's talk about those units. A unit is a standard quantity used to specify a measurement. So if we want to measure how long a piece of wood is, and I say it's 5, that doesn't tell us anything, right? We need to know 5 meters, 5 inches, 5 feet. There are different systems of units. The two most common are the metric system and the English system. The English system is inches and pounds and things like that. And that's what we typically use in American culture. The metric system is used in most of the rest of the world, and we Americans are just really stubborn and not getting on board with that. I hope to convince you that the metric system, once you become familiar with it, is far superior to the English system. Scientists use the international system of units. It is based on the metric system. There are some very, very minor differences. For our purposes, the differences are nothing. There's no difference. So I will use SI and metric interchangeably. The units are exactly the same. Really, the only difference is what they define as the base unit. And I really don't care what the base unit is. Some standard base units in the SI system. Some of these we'll use. Length is measured in meters, mass in kilograms, time in seconds, temperature is measured in kelvins, and amount of substance in moles. These last two we won't get into in this class at all. The abbreviations are significant. We never use periods in the SI or metric system, and capital or lowercase is significant. So we have to, pay attention to details there. It's a little bit like a password. You try to log into some website, and the password is case sensitive, right? That means if you've got a capital M or a lowercase m, one's correct and the other's not. And that's the way unit abbreviations are. They are case sensitive. I'm going to go through these slides pretty quickly, just more for interest. It's helpful to know roughly how large these metric units are so that you can identify whether your answers are reasonable or not. A meter is a little longer than a yard. And then there's how they are defined. They recently changed some of the definitions, so these slides might actually be out of date. Mass. Mass and weight are slightly different. Weight is the pull of gravity on an object. It's actually a unit of force. Mass is actually the quantity of matter in an object. As long as you stay on the same planet, you don't change your gravity, then you can use them interchangeably, but there is a difference. The SI unit is a kilogram. A kilogram is a little over 2 pounds. What we use most commonly in chemistry is the gram, and a gram is 1/1000th of a kilogram. So a gram is a small quantity of matter. For many things, it's about the size of a green pea. Seconds we're familiar with. This is a measure of time. Kelvin is the SI unit of temperature. We talked a little bit about energy. Temperature is a measure of the average kinetic energy of the atoms or molecules in a piece of matter. Temperature also helps us to predict the direction of thermal energy transfer. We know from personal life experience that heat moves from a hot thing to a cold thing. right? And eventually they'll come to the same temperature. So temperature measures the amount of kinetic energy in an object. So what about these temperature scales? So here we have 3 thermometers, Fahrenheit, Celsius, and Kelvin. Fahrenheit is the English unit of temperature. When you hear the weatherman saying it's going to be 65 degrees today, he's talking about degrees Fahrenheit. Celsius is the metric unit, and this is what much of the world uses. In Europe, they might say, well, it's going to be 24 degrees today. Well, that's actually a rather pleasant day. It'd be in the 70s Fahrenheit. They're talking in Celsius. So when we measure temperatures in the lab, we're going to be using the Celsius degree because that's how the thermometers are calibrated. The Kelvin temperature scale is based on absolute zero. The metric scale, the Celsius scale, is based on 0 being the freezing point of water and 100 degrees being the boiling point of water. Those numbers on the Fahrenheit scale are 212 and 32. Those have their own historical reasons that we don't need to know about. On the Kelvin scale, the 0 is absolute 0. It's not possible to have a negative Kelvin temperature. The Celsius degree and the Kelvin, and it is a Kelvin and not a Kelvin degree, the Kelvin, they are the same size, and so the difference between these scales is just they're offset by 273. So here is 0 degrees Celsius, that would be 273 Kelvin. We need to be able to convert between temperatures because sometimes we'll get temperatures reported in Fahrenheit. We need to convert them to Celsius. We'll need to convert Celsius into Kelvin and vice versa. So temperature conversions are done with equations. There's really no other way to do it, and these are the equations right here. You should memorize these equations, especially the Kelvin to Celsius one. It's not that hard, and that one gets used a lot. We don't use the Celsius Fahrenheit one as much. So to take a Fahrenheit temperature and convert to Celsius, you take the Fahrenheit temperature, you subtract 32. That's to adjust for the difference in where the 0 is. And you take that quantity and you divide by 1.8. And we'll get some practice doing that on the worksheet. Kelvin, you just take the Celsius temperature and you add 273.15. So let's practice. Gallium's a solid metal at room temperature, but will melt to a liquid in your hand. Really cool thing. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and the Kelvin scale? So we need to convert Fahrenheit to Celsius. So we need to use equations. So for part A, we're going to use the first equation. The temperature in Celsius is equal to the temperature in Fahrenheit minus 32 divided by 1.8. Since we're calculating Celsius, we can just plug that Fahrenheit temperature into our equation. If you have your calculator, which you should, get it out. So we've got 85.6 minus 32 divided by 1.8. Need to be careful to communicate correctly with your calculator. 85.6 minus 32. Press the equal sign. It should show you 53.6. I don't need to write that down, but then I'm going to divide that by 1.8. And my calculator is going to show me 29.77777, on and on and on. 29.77 repeating. We're going to learn about significant figures today, but for temperatures, just look at your original temperature. This temperature ends in the first decimal place, so we're going to take this temperature and stop it in the first decimal place as well. So we're going to stop right here. The next digit is higher, is 5 or higher, so we're going to round this to 29.8 degrees Celsius. Okay. If your calculator is not giving you that answer, then we need to speak with your calculator, right? Because it's always the calculator's fault. But you have to get that calculator in line. Any questions? And then it asks us to convert this temperature to the Kelvin scale. So you're not given an equation that relates Fahrenheit and Kelvin. You could come up with one, but nobody would use it. We have already converted the Fahrenheit into Celsius, which is what needs to be done, and now we can take the Celsius and convert that into Kelvin. So Kelvin temperature is equal to the Celsius temperature plus 273.15. So we take that 29.8, we add 273.15. And I'm getting 302.9. Well, you're probably getting, yeah, let me do that again, because I kept the whole number, 29.8 plus 273.15. You're going to get 302.95. And again, our original number ended in the first decimal place. We're going to round this to the first decimal place. So rounding the 5 makes the 9 go up to a 10, and so then we're going to get 303.0 Kelvin. We'll get more into the rounding and how many digits to write down. Any questions about how to use the equations? Yep.
Just a question. If I were to put just 303 Kelvin, that would be marked incorrect, correct?
It depends. So the question is, if you wrote 303 Kelvin, would that be marked incorrect? If the question has to do with significant figures, it could be marked incorrect. And we'll learn more about that. But as close, which is the most important thing. Any other questions? So the metric system uses prefixes to change the size of the units. We need different sizes of units because, like, I live in Reedley and I commute to Fresno and it's roughly 30 miles. We use the unit mile to measure that because if we did it in inches, it would be a ridiculously large number, right? And yet, if I wanted to measure the length of my iPad case, I wouldn't want to measure this in miles, right? We want to use a unit that is similar in size to what we're measuring so that we can deal with reasonable numbers. So the metric system and the SI system do this by taking their base units, meters, grams, etc., and putting a prefix in front of them to make them larger or smaller. And all of these multipliers are powers of 10. The metric system is based on tens. And I've given you a list of these in the memorization quiz material that you should be working on memorizing. Once you memorize those prefixes, the metric system's a piece of cake. So if we have kilometer, sometimes pronounced kilometer, that prefix kilo means 1,000 or 10 to the 3. So when we put kilo in front of meter, that makes that unit 1,000 times larger. So 1 kilometer is equal to 1,000 meters. We can also write that as 10 to the 3rd meters. Okay, so the prefixes are just used to make the units larger and smaller. So there's a lot of them. I think there's even more, but we don't use all of them in chemistry. Excuse me. Most important ones, milli, micro, kilo, millicenti, kilo, micro, sometimes nano, sometimes mega. Those are the most important ones. We can't always do everything that we know that we should do. Sometimes we just have to do some and be good enough. So if you don't have it in you to memorize all of the metric prefixes, at least get those, okay? It's only 6. We want to know the name of the prefix, how to spell that. We want the abbreviation, the symbol. Mega is capital M because it makes the unit bigger. Milli is lowercase m, it makes the unit smaller. And then we ran out of m, so we used the Greek m, micro, and that makes it even smaller. C for centi, K for kilo, N for nano. So they're not trying to be confusing. These multipliers written out in decimal notation make a kind of nice pattern there, but they're not very useful because so many zeros. So these are the ones we want to look at over here. We want to remember that mega means 10 to the 6. Kilo means 10 to the 3. Most of these are multiples of 3 in the exponent. Centi is 10 to the minus 2, that's a weird one. 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. Okay, so you just have to memorize them. You all learned the alphabet. You can do this too. Okay, so how long is 4.5 megameters in meters? Well, we don't even need to use a calculator for this. We just need to know, what does that capital M represent? And so maybe we haven't memorized that yet, but that capital M represents 10 to the 6. So 4.5 megameters, we can express that capital M as times 10 to the 6. Times 10 to the 6 meters. So the M is just an abbreviation. In fact, let's call it times 10 to the 6. The capital M is just a shorthand way of saying times 10 to the 6. So I can convert this megameters into meters just by writing what that prefix is standing for. Does that make sense? I don't want to lose anybody yet. I made a mess down here. Here we have a unit without a prefix, liters, and it's asking us how many nanoliters would that be? Well, what does the prefix nano mean? Nano means times 10 to the what? Times 10 to the minus 9. Nano, 9, nano, they kind of go together. So nano means 10 to the minus 9. So we take this number and, oh look, it has a times 10 to the minus 9 in it. So instead of writing that, we can write the letter N. So that in nanoliters is 7.13 nanoliters. This N stands in for times 10 to the minus 9. It's like a code. Okay? Any questions? Other units are derived from the base units. There are combinations of other units. So, you talk about how fast you were going on the highway. That's a rate of speed. You say miles per hour, or in the metric system we might say meters per second. There's not really a simplification. There isn't a special unit for that. We just use two units together. Those are derived units. So ones that are important in chemistry, volume. We measure volumes. That's a measure of space. I think we understand that. If you take a unit of length and cube it, it becomes a unit of volume. So, if you have a rectangular solid and you want to know the volume of it, from geometry, we know that the volume equals the length times the width times the height. Yeah? If we measure each of those in meters, length in meters times width in meters times height in meters, algebra tells us we can simplify that and call that meters cubed. Something raised to a power, the power says, this power of 3 says that it's meters multiplied by itself 3 times. So cubic meter, cubic millimeter, cubic centimeter, any length unit cubed. We can also do cubic inches and cubic feet, but we don't use English units in chemistry. We also have units that are more typically used to measure volumes of liquids, and those are the liter and the milliliter. We have units like this in the English system as well, gallons and ounces and quarts, things like that. There are relationships, though, between liters and cubic meters. So if we look at this cube has 10 centimeters on a side. It's a cube, so it's also 10 centimeters high and 10 centimeters deep. So the volume of this in centimeters, 10 centimeters times 10 centimeters times 10 centimeters, that's going to be 10 to the third cubic centimeters, or 1,000 cubic centimeters. That make sense? If we divide this along the white lines, each of these little cubes is 1 cubic centimeter. So in this big box, we have 1,000 of these little boxes. Okay? That's me sitting inside of a box that is a cubic meter in size. So that's 100 centimeters on each side, bigger than the one we were just looking at. It's helpful to have an idea of how big is a cubic meter. A cubic meter is pretty big. You can sit in it very comfortably. Okay, relationships between some of the units, conversion factors. So this is a table that is going to be very useful to you. Pretty much any of the metric or unit conversions, period, that you are going to do in homework or on exams or anything, you should be able to do them just using these conversions, these relationships. Okay, I know that you can Google and find out, the relationship between any two units, but part of what we're going to do when we're learning to convert units is we're going to use a technique called dimensional analysis, and that technique is going to be important for some other things that you won't be able to ask Google about. So I know that you can do these unit conversions another way, but I want you to try to learn my way, okay? I've been doing this for a long time. It really does work. So here we've got different lengths, and most of these are going to be relationships between the metric system and the English system. This one is important. You should probably memorize that one because we will use that one fairly often. An inch is 2.54 centimeters, and that is an exact conversion. For mass, we've got kilograms and pounds and ounces and all of those relationships here. And volume. So 1,000 cubic centimeters, that's what we just looked at back here. This was 1,000 cubic centimeters, right? That is a liter, 1,000 cubic centimeters. So a liter is 1,000 milliliters or 1,000 cubic centimeters. And what's not listed on here, and students often forget, 1 cubic centimeter is the same as 1 milliliter. So these are two names for exactly the same thing. A milliliter is exactly the same as a cubic centimeter. One is measured, length, width, and height. The other is more of a volume measurement, but they're the same volume. And then we've got some relationships here as well. The metric relationships, other than liter to milliliter, aren't given here because we don't need them. We don't need to be shown what milliliters to kiloliters is because we just use the metric prefixes. Density is another derived unit, and you should have all heard about density before. Density is the mass of a substance divided by its volume. Or we can shorten this equation, D equals M over V. And you should know that one. D equals M over V. We can measure density of solids or liquids or gases. Common units for liquids and solids, grams per milliliter, grams per cubic centimeters. Gases are much less dense, so we tend to use grams per liter. Density is a physical property that does change with temperature. It depends on the temperature. So let's think about that. If the density changes with temperature, that means that the mass and or the volume must change with temperature. Do you think the mass of an object changes if it gets warmer or colder? No. Mass is a measure of how much matter is in the object. That doesn't depend on temperature. What about volume? Volume can change, right? So when you heat something up, typically it expands. Sometimes it might just be a very minor thing that you don't necessarily notice. When you cool something down, typically it will get smaller. So density depends somewhat on temperature. And I'll tell you, here's a hint for the future. There's a lab where there's a post-lab question that asks you about this very thing. What about the density and the temperature and why? Okay, density depends on temperature because the volume changes with temperature. Okay. Oops, I should have done this. Here we have a table of densities of common substances at 20 degrees Celsius. The temperature is specified because if we're going to be detailed, we need to know what temperature because it'll change slightly. Here we've got ice. The density of ice at 0 is 0.917. The density of water at 4 degrees Celsius is 1. And so here we see that a temperature change of 4 degrees Celsius causes a measurable difference in the density of water. You do not memorize these except for possibly water. Water in general has a density of 1 gram per milliliter. It's not a coincidence. The units were kind of set up that way. The rest of these you would just look up. So density is a property, right, of a substance. It's a physical property because you can measure the density without changing what the substance is. We can also define properties as being intensive or extensive. So an intensive property does not depend on the amount of substance. So you can think of it as an intrinsic quality or something internal. It doesn't matter how much of the substance you have, that property is always the same. So if you think about taking the temperature, say, of some ice cream, I don't know where that came from. If I take and cut that chunk of ice cream in half, does the temperature change? No, temperature's the same. Does the color change? No. Those are intensive properties. Density is an intensive property. It doesn't depend how much stuff. A small piece of wood floats on water. A large piece of wood also floats on water because the density of wood is less than the density of water. Extensive properties are external. They do depend on the amount of substance. So the mass of an object, that lump of ice cream that I cut in half, if I weigh it, the piece that I cut off weighs less than the whole thing. The weight changed, the mass changed because I cut it in half. Length, volume, those sorts of things will change with the amount of substance. Intensive properties can sometimes be used to identify what a substance is. Density is one of those things that you can use to identify a metal. So let's do this example here, calculating density. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? We're going to have a lot of problems that fit this pattern. This is, when I was growing up, they called this a story problem. That sounds more friendly. Now they call them word problems. There's a whole bunch of words in this problem. And what we really need to do is we need to take the numbers and do some math, right? So you should always read the whole thing and then look at the numbers. Go fish out the numbers. So let's just pull the numbers out with their units. So there are two numbers in that problem. 3.15 grams, 0.233 cubic centimeters. And then ask ourselves, what are we trying to do with this? This question does not say, find the density of the ring. It says, is the ring made of platinum? And so you need to make that leap and say, well, what could I do with these numbers? I could calculate the density and compare it to the density of platinum. If they're the same, the ring is made of platinum. If they're different, it isn't. So we need to calculate the density. Density is something we need an equation for. So we need to get the equation. D, density, equals m over v, mass over volume. So now we can look at these numbers we were given and identify what are these quantities. Well, they actually use the word mass here, mass of. So this is the mass. And then here it talks about displacing water. So if you take just a glass at home that you would drink out of and fill it to the very top with water, and then, let's see, what could we put in there? I don't know. I'm blanking. Marbles. And then you put 5 marbles into the glass of water. What's going to happen? Water's going to spill out because the marbles are taking up some space inside the water. So they're going to push out a volume of water that's equal to their volume. So the volume of a irregular shaped object, or any object really, can be measured by seeing how much water is displaced by it. So what they're telling us here is that the ring has a volume of 0.233 cubic centimeters. We could also infer that from looking at these units. A length unit cubed is a unit of volume. So this is the volume. We're trying to find the density. We need the mass and the volume. Oh, look, there's the mass and the volume. So when you're showing your work, if there's an equation involved, you should write out the equation. And then you write out the equation with the numbers and their units in it. So we're going to write the mass up here, 3.15 grams, divided by 0.233 cubic centimeters. And then we'll do the math.
So we're just dividing 3.15 to 0.
Yeah. Getting a phone call. 3.15 divided by 0.233, and then my calculator is going to give me a bunch of numbers. We'll talk later about why I'm calling it 13.5. What happens to those units? Do they cancel out? No. So we just write them down. So that's grams over cubic centimeters, which is a unit of density. So that's the density of the ring. Is it platinum? We have to compare it to the density of platinum. So let's go back here. Density of platinum's way down there at the bottom, 21.4. 13.5 isn't even close, right? So is this platinum? Nope. So this question is asking, is the ring made of platinum? This was necessary to find the answer, but that's not the answer. The answer here is no. Always make sure you're answering the question that was asked. Any questions? Okay, so the woman in this example is shocked that the ring is fake and returns it. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? Well, we just did a problem like this, so this one should be a lot easier. We need to calculate the density, right? Density is the mass divided by the volume. And since we're now familiar with this kind of problem, we see, oh, there's the mass, 4.53 grams, and we're going to divide by the the volume, 0.212 cubic centimeters. 4.53 divided by 0.212, 21.4 grams per cubic centimeter. Remember when we looked it up, it was 21.5. That is very, very close. And we'll be talking about uncertainty in measurements. There's error in every measurement. So the fact that we got 21.4 and the actual density is 21.5, that difference is not significant. This ring is made of platinum. Any questions?